You're already familiar with the idea of relative extrema, in other words, relative maximum, relative minimums. Now we want to extend this to the idea of an absolute extrema, an absolute maximum, an absolute minimum. It's really pretty simple. The largest value of a function, if it exists, is called the absolute maximum of the function. And the smallest possible value of a function, if it exists, is called the absolute minimum. And I guess a picture's worth 1,000 words. If you have this function, you can see that there's a point that is higher than any other point on the curve. The y value of that point is what we call the absolute maximum. There is no point on that curve any higher than that. So at x sub 2, you have whatever the y value is, we'll call it f of x sub 2. That y value is the absolute maximum. Now be careful, because some people write the entire point. That's the point x sub 2 comma f of x sub 2. But the point itself is not the absolute maximum. The absolute maximum is the y value. The y value is the height. The absolute maximum is the y value. It occurs at a certain x value. In fact, you could say the absolute maximum is whatever f of x sub 2 is. We'll just call it f of x sub 2 in general. But it occurs at the corresponding x value. So it occurs at x equal whatever x sub 2 is. And by the same token, if there's a point on the curve whose y value is lower, less than any other point on the curve, less than or equal to any other point on that curve, that's called an absolute minimum. So at x sub 1, whatever that y value is, we'll just call it f of x sub 1. That y value, not the point itself, but just the y value, is the absolute minimum. So we could say the absolute minimum is f of x sub 1. In other words, this y value. And it occurs at x equal whatever the x coordinate of that point is, in this case x sub 1. It's a very simple concept. I do want to formalize it a little bit by giving this definition. If a function f is defined on an interval and c is a number in that interval, then f of c, the y value at x equal to c, is the absolute maximum of the function on the interval if f of x is less than or equal to f of c for every x in the interval. In other words, if you calculate the y value for that x value at the maximum, there is no other x value when you calculate its y value that's any bigger than that y value. And conversely, f of c is the absolute minimum of the function on the interval if f of x is greater than or equal to f of c for every x in the interval. In other words, if you calculate the y value of that minimum at x equals c, it comes out less than or equal to any other y value that you can calculate in that interval. That's the formal definition. Intuitively, it's easy to see, but that's the way we'd formally just define it. I might also say that in terms of just vocabulary, sometimes we lump maxima and minima together and just call them extrema. So we can say the absolute maxima and minima together are the absolute extrema. And occasionally we need the word, the singular of that word. The singular of extrema is extremum. So just a little vocabulary lesson there. Just to bring the point home a little better, I just want to look at a couple or three examples here actually, and just say again how simple this is when you have a graph. if you have this function and you're looking at it, there's a point whose y value is greater than or equal to the y value of any other point on the curve, and that occurs here. So the absolute maximum occurs at x of 1. Now be really careful, because if you take x of 1, plug it into the function, you're going to get f of x of 1. The y value is the absolute maximum. It's not a point. The y value of the point is the absolute maximum. By the same token, if you're looking at this curve, there's one point whose y value is less than or equal to any other y value on the curve, and that's here. So there's the absolute minimum, and again, the absolute minimum is the y value itself. So at x sub 2, whatever f of x sub 2 comes out to be, that is the absolute minimum. So the absolute extrema are y values. You don't list the entire point. When they ask for the absolute max or absolute min, you give the y values corresponding to those points. And again, if you have a function like this, there are no relative extrema. So on a continuous function over an interval, if the curve just keeps increasing from left to right, the left-hand endpoint is going to be the absolute minimum, and the right-hand endpoint is going to be the absolute maximum. And if it were decreasing, it'd be reversed. So there's no relative extrema. It's pretty simple to see that the max and mins are going to occur at the endpoints. So we would say whatever you get when you take x sub 1 and plug it into the function, call it f of x sub 1. That's the absolute minimum. And when you take x sub 2, which is the right-hand endpoint, and plug it into the function, you get f of x sub 2. That y value is the absolute maximum. And continuing over here, you can see that there is no point on the curve any lower than this one. So the y value at x sub 3, which is f of x sub 3, is the absolute minimum. And there is no point any higher than this one, so the y-coordinate of that point, which would be, that's x sub 4, so that would be f of x sub 4. That is the absolute maximum. And belaboring that point, the maxes and mins are actually y values. There's not the whole point, it's the y value of that corresponding point. This kind of leads us to something that's very important. It's called the extreme value theorem. The extreme value theorem says a function f that's continuous on a closed interval a to b will have both an absolute maximum and an absolute minimum. Now this is very important, but it has two conditions that have to be satisfied. The function has to be continuous. Intuitively, that means you've got to be able to trace out the curve without lifting your pen from the paper. And it has to be on a closed interval. Closed, closed. And you can see that it's got to be true. If you've got to draw the curve from here to here, and you can't lift your pencil from the paper, it's pretty easy to see that there's going to be a max somewhere and there's going to be a min somewhere. And that's all the extreme value theorem says. Now, just as an aside, the max might be the absolute max might be at a relative max, or it might not. The absolute min may be at a relative min or not. In this case, the absolute max is at a relative max, and the absolute min is not. It's at an endpoint. If you have the graph, you have it made, because that tells the story once you have the graph. Now, I want to end up my little intro to this topic by showing a violation of the extreme value theorem. As long as the function is continuous on a closed interval, the extreme value theorem applies, and you're assured of having a max and a min. However, if one of these conditions or both are not satisfied, you may or may not have absolute extrema. For example, here, the function is not continuous. You can't draw this curve without lifting your pen from the paper. So this doesn't apply. So you don't know if you have an absolute max or a min or not just by knowing that you have a discontinuous function. But by looking at the graph, you can see there is a low point. So the y-coordinate here at A, that f of A, that would be your absolute minimum. But there is no absolute maximum, because no matter what you do, however close you get to that open circle here, you can't get to a point that's any higher than the other point. Because just say that y value is really close to 2.99. Well, I say, well, that's as big as I can get. No, you could go to 2.999 or 2.999999 and add as many nines as you want. The fact of the matter, with an open interval, you can keep getting closer and closer just by adding another decimal place. So there is no absolute maximum, because there is no point whose y value is higher than every other point in the curve. It's not a violation of the extreme value theorem because you have a discontinuous function on that interval. This other example, it's a continuous function, but it's not on a closed interval, because a closed interval would have to have the dots would be closed. In other words, that curve would actually hit this vertical line at A and at B. But this is open. So in order for it to be a closed interval, it'd have to be like that. It'd have to achieve the value at A and at B, but it doesn't. This is actually an open interval. You can get as close to A as you want, but you never actually get there. You can get as close to B as you want, but you never actually get there. This is an open interval, not a closed interval, so the extreme value theorem doesn't apply. So again, you may or may not have absolute extrema. Now you can tell from the graph that you have a minimum, because there's no y value any lower than the one at x sub 1. So at f of x sub 1, you have an absolute min. But you don't have a max, because it just keeps going up. And if the graph were flipped, you'd have a max but no min. The point being, if you have a discontinuous function over the interval, or if the interval is not closed, the extreme value theorem just simply does not apply.